So computationally, we have, when you describe materials, really from a molecular perspective. So you have traditionally you have the chemists that tell us this is the molecular structure of a material. Then you have the engineers tell us, well, this is the strength of a material. And there's a huge gap between these. So you cannot predict using traditional models. If you go to college today, you wouldn't learn how to predict the strength of a polymer or metal or steel or any kind of material from knowing just the chemical structure. There's obviously something between. And these what's in between are scales that are huge, vastly different scales. And you can compare this with the size of the universe or distance to the moon. There are orders of magnitude in length scales between 10 to the minus 10 angstrom, which is the scale of a chemical bond, and something, say out of a meter or 100 meter, like an airplane or ship or building. So now you get 10 to the minus 10 to the minus 10 to 10 to the 0 orders of scales difference. And how do you bridge these? So there, obviously, if you simulate materials, right, and you say, let's simulate every single atom, so now you got trillions and trillions and trillions of atoms that you need to simulate, and that's beyond the capability of a computer, right? So you would basically have to predict the motion of every single atom. Now that sort of problem requires us to think about new ways computationally and modeling-wise how we deal with this problem. And so how we can do this now is we can still use really big computers to simulate ever larger systems, right? Larger molecules, more complex molecules, better models for the chemical bonds between the molecules. But we also have methods now in which we can upscale things. So we group atoms and molecules into functional units, right? So you can assume that several molecules form a fiber, and this fiber has a certain behavior, and then we can model the behavior of the fiber embedded in a larger group of fibers using a computationally simpler technique. And that technique really, it's called multi-scale modeling. And what's unique about this technique is we can base it really on the atomic scale interaction. So we start in the beginning from the description of chemistry. We put together atoms and molecules. We simulate how they behave. We then identify emerging behavior in these groups of atoms and molecules, and we coarse grain this. We call it coarse graining, computationally simplifying the interactions. In sort of similar way, as you imagine, if you imagine a chemical bond, which you in chemistry sometimes think of as a spring, in a simple way. Now, in a quantum mechanical description, the spring really comes from electrons interacting with the atom core and other structures in the system. So these interactions, very complex features, really can be described by a simple spring, right? And this is something that we can do again and again at different scales to solve this problem. So big computers is one. New ideas, understanding about how we can model chemical bonds effectively without actually solving all the complex quantum mechanical equations is very important as well. And then we need to validate, and that's when experimental studies are going to come in, because we can predict things, we can build models, but if we don't have a good tool of actually making sure that what we're doing is correct, we need experimentation at different scales that tell us that this approach of actually grouping atoms into a functional fiber that we have identified makes sense. We need to prove this, and that can be proven by using experimentation. And so we use this systematically. Once we gain understanding for systems, wide variety of systems, we can apply this to even more systems, right? And then we have confidence that the tools we have are actually predictive. And so we now have various examples where we've actually used these types of computational predictions for materials like carbon nanotube-based fibers. We've used it for spider webs, other protein materials, engineered materials, and we're very successful actually in predicting phenomena that we can see in a simulation and an experiment. And there's sort of advantages of both worlds, right? We can see things in experimentation, we can see them, and there's immediate proof that that really happens. In a simulation, we might be able to see additional things. We might be able to see very low resolution motion of atoms, which are very hard to see experimentally. We can design conditions in a simulation that we cannot easily probe in experimentation, right? Extreme pressures, we can invent material behaviors, we can probe what if silk would behave in a very particular way, which helps us really understand the system in a very systematic way. So that combination of experiment, simulation, the talking between them, validation, and asking questions that again are informed from the simulation results, from the experimental results, is what drives the research. And what we do in the end, by combining then simulation experiment, we can build theories. And that's sort of the final goal always, is that we don't want to end just by, you know, sort of putting forth some predictions we've made or some observations we've made, but actually we like to understand things, and you can build a model, an equation or a graph, something of that kind, mathematically actually describe the essence of what you see in the material. And that's usually the goal. Most projects, most the things we look at in our lab work like this. So we start simulation experiment, simulation, pushing things forward, eventually ending with a model that captures really the essence. And that's what's useful for engineers in the end.